Hello and welcome back to Physical Geology. I'm Robert Lopez. Today I want to go over the eScienceLabs.com website that you'll need for the Geology Lab Kit. Now here I am at eScienceLabs.com. Once you get your account and you log in, what you want to do, you want to go to the student portal right here. So click on Student and that'll take you to this page. And you'll see that near the bottom here are the different kit resources, right? So your kit is for geology. And remember, our geology kit is custom order, so we're not going to have all the labs in this lab manual. So essentially, this is the manual, the lab manual for the geology lab. So you click on the geology link here, and then these are the different labs that are in this manual. Obviously, we're not doing all of them because we have a custom kit. The first lab we're doing is building a planet here, and that's on plate tectonics. So click on here and it'll take you to the building the planet lab. And part of it, they talk about the Big Bang and the origin of the universe, origin of the solar system. I do a lot of this as well in my video lectures. Another thing about this pre-lab is there are some errors in it, and I want to make sure I point those out to you in this video here. So this first animation just describes in general what the Big Bang is and a little bit about plate tectonics. You'll see that I go into it more deeply in my lectures. Then there's an introduction here. Here's more on this Big Bang. So you read through that, but I recommend looking at my videos. So don't spend a whole lot of time on this material here. They put this little applet on here. It's kind of fun. You can play around with some parameters for asteroids and planets and see how they orbit and they go around the sun. But it has no reference to what we're doing here. All right, this is more for astronomy. I don't understand why they have this in there. So I wouldn't even bother or waste my time with this right now. Remember, the Big Bang postulates that the universe began at a single point. And that concept is called singularity. And then they go into these layers of Earth, right? Now, there's a problem here is that there is not a vast ocean of magma under our feet. That's untrue. Part of the problem with this introduction is that they refer to the mantle as being mostly molten, when in fact it's solid. The mantle is solid. It's under tremendous pressure because it's deep in Earth. And remember, pressure inhibits melting, right? Even though it's hot, it's solid. And you'll see in my lectures, I have graphs and tables that I show you how this works. But just know that the mantle is not molten. There may be portions of it that are, in fact, they do say semi-molten here. And that's something called the Asthenosphere. So we'll talk about that Asthenosphere. One thing that I do want to point out, which I like what they do here, they describe the Earth into these physical or chemical layers. And so the chemical layers, those are the ones that I usually talk about first. That's the crust, the mantle, and the core. And they differ in chemistry in that the core is primarily iron and nickel metal, very dense. It's a density of anywhere from 10 to 13 grams per centimeter cube. It's far denser than the other layers of Earth. The middle layer, called the mantle, is composed of a silicate rock, primarily a rock called peridotite, and this peridotite is primarily rich in magnesium and iron, right? So there's lots of magnesium and iron, some chromium as well. So a little bit difference in chemistry there. And finally, the crust, the outer thinnest layer of Earth, is composed also of silicate material, but there's more calcium, there's more sodium, more potassium in these rocks. Compared to the mantle and the core. So that's the chemical differences, or the three fundamental layers of Earth, these chemical layers. The physical layers, well, now within these chemical layers, there are other boundaries. For example, they do have them in here. There's this lithosphere. The key thing I want you to know about the lithosphere is this Greek word lithos means stone in Greek. And the lithosphere, which comprises the crust plus the uppermost mantle, those are the tectonic plates. So whenever you see the word lithosphere, we're talking about tectonic plates, which are really kind of a hybrid of crust plus the uppermost mantle, right? And then the asthenosphere, here's another Greek word. This Greek word astheno means weak or debilitated. So it's a weak, soft layer. It may be partially molten, right? It's ductile. Ductile is a word which means it flows like plastic, right? Flows like plastic here. And there may be areas of the asthenosphere that are molten, but for the most part, it's solid, but it has a really strange behavior. It's what we call a visco-elastic material. Viscous because it kind of behaves like a liquid, very thick, but also elastic in that it behaves like a solid. So it's strange. But the key thing about the asthenosphere, it's a weak sphere of Earth. It flows, it moves around, which allows the overlying lithospheric tectonic plates to move. So that's an important concept here, is think of this asthenosphere as a lubrication for plate tectonics. Then this mesosphere, well, that's everything else in the mantle. From the base of the asthenosphere all the way down to the core is our mesosphere. And then we got the outer core and the inner core. And you'll see that the outer core is a molten liquid. And we know that because of how certain type of earthquake waves travel through, or actually don't travel through the core. They stop because these earthquake waves do not travel in liquids. That's kind of an important thing to say, is that they're called S waves. These secondary seismic waves do not travel through the core, which means the outer core must be liquid. However, we know the S waves do travel through the asthenosphere and the rest of the mantle, which tells us that it's solid. Right? So in my lectures, I talk about something called the S wave shadow zone. So that's our inner core and outer core, and then we talked about the chemical layers a little bit. Then there's a little bit of background on plate tectonics. I want you to read what's going on here. And then I couldn't get this thing to run either, but on the Canvas website, I have plenty of animations and things you can look at, and also look at my YouTube videos. I have some examples of how these tectonic boundaries occur. And then here they talk more about the tectonic boundaries. Remember that the three types are the convergent, divergent, and the transform boundaries, right? And then they talk about faults. You want to read about this. Remember, a fault is a fracture in a rock where slip occurs, or offset. See how the layers are offset? And we call that slip. And when we look at faults, there's really two fundamental types. There's one that's slip in the direction of dip. So dip is this angle from the horizontal here down to the geologic fault zone, right? So this angle here would be the dip angle. So it's dipping or inclined. And note that this particular fault is slipping in that dip direction. So one type of fault is a dip-slip fault. The other type of fault is down here, which moves parallel to the fault zone here, right? And so note that it's a horizontal slip, and this horizontal direction we call strike. And strike is really a compass bearing, right? So in this case, this fault is striking to the west of north. So you'd say northwest. So, and note that it's slipping in that direction. So this would be a strike-slip fault. For example, the San Andreas fault is a strike-slip fault. And then you'll see that for the dip-slip faults, there's one called a normal fault, and another one down here called a reverse fault. But the key thing is the way we describe these. There's something called a hanging wall and a footwall. So make sure you read through these and understand what these refer to. In fact, I wanted to point out when they talk about the footwall and hanging wall, they use the wrong word here. There must have been a typo or something. This should say hanging wall. So you got to observe the hanging wall and which way it moves, whether it goes up or down, and if it goes up, it's called a reverse fault. If it goes down, it's called a normal fault. So read about what's going on there. And then for the strike-slip faults here, there could be some that are left lateral or right lateral. It depends on which direction they move. So look at the animation and follow through there. And so remember, a fault is a fracture in rocks where slip occurs, or offset. And then they go into earthquakes here. Remember, where tectonic plates rub against each other, pull away from each other, crash into each other. Well, that's where we see the earthquakes. So really, earthquakes occur along these seismic belts, right? These which are the plate tectonic margins or boundaries. you can read about the anthropogenic factors, how, especially fracking can cause earthquakes. You can read about that. And then this is a quiz. I wouldn't even bother with this quiz. One of the problems with the quiz is some of the answers are impossible. So this first one's a fault. For this one, no matter how I order these, I can never get it correct. So I can never advance beyond question number 2 here. I know that the continental crust is the highest. It's at the surface. It's the least dense. Then it should be ocean crust. Then we know that collectively the upper parts of the mantle plus the crust is a lithosphere. And I said the lithosphere directly overlies the asthenosphere, which all this makes the mantle, right? And then obviously in the middle is the core. But when you do it this way, and this should be the order, it tells you it's wrong. I've tried to do this in different orders. I can't get the right answer. Don't even bother with this quiz. In fact, don't waste your time on that. That's not even graded. And now the important part here is, here are the files. So these are the files you need for completing this lab. So you'll click here, download these files, and then you'll be good to go. In fact, let's just look at this one here, the protocol. And so on this one, you can see it gives you the directions, what you need, the procedures, how you want to need to mix the materials. You're basically, what you're making in this lab, you're making a asthenosphere. You're making this goopy material that essentially has the texture of icing or frosting, right? So that's kind of the goal you want. So you'll have to add more or less water in it to make it feel like icing or frosting. Then you cut out the styrofoam plates here, and you want to label them to, India, Eurasia, or the Mid-Atlantic Ridge, and then you'll move them on this asthenosphere that you created out of the salt and flour, and to see what happens, right? And you describe. But one of the key things I want you to do here, and the lab describes it, as you're doing these labs, you want to take photos of your, for example, take pictures here of your results, and you want to include those photos in your lab. So when you submit your lab, include the pics. Take them with your phone, right? Put them in the file, send me the pic. I want to see the results of the lab there, right? So you can see that there are other files you need to do. So you'll need to complete all of these forms and submit to the Dropbox by the due date of this lab. And then you can see here that the next lab would be the mineral or rock ingredient. So the same thing goes along with this lab, where you follow the same objectives. You look at the animations here. They talk about chemical elements. There's a lot of good material that I discuss in my lectures. You see them here as well. So read through this material, and it'll help you with identification of the minerals, because you get a series of minerals. In fact, here are some data tables that, based on what physical properties you get from your mineral samples, how you test them, you compare them to these tables here, and then you can identify the minerals. So it's key to have these, because if you don't have these data tables, you're not going to be able to identify the minerals, right? So you need this material here. That's your basically, this is your guide of how to identify minerals right here for this particular lab. And then there's some more animations and videos. And then again at the bottom, here are the lab sheets, right? So there we go. And then there's igneous rocks and volcanoes for the following week. All right, well, let's stop here for now.